Exercise 19. This is another one that I've had to re-record because I didn't read the definitions. So these you have to be really careful because they're really counterintuitive the first time you see them, but I don't know, they're kind of neat once you get to know them. So anyways, we're going to start with proving this statement. And so first, let's see here. So we're going to say to prove this direction, let X be the disjoint union of A and B, where nu of A is 0, as is mu of B. And this is because we're assuming that nu is mutually singular with respect to mu. So then, by 3.13a, we have nu of A is less than or equal to nu of A, and likewise mu of B is less than or equal to mu of B. So let's see here, what do we know then? Well, we know that nu of A and mu of B are 0, and the absolute value of nu of A has to be a positive number. So this implies nu of A equals mu of B equals 0, and thus nu is mutually singular with respect to mu. Ooh, is this the correct direction? No, I prove the other direction. Because what we did is we started with the absolute value of nu A equals absolute value of mu B, well, total variation, whatever. But we started with this. So that's why you don't want to flip the order when you're writing down these notes, because then this will happen. For this direction, we need a lemma. That will be as follows. If for all, okay, let's let A be in whatever sigma algebra we're working on. So if for all E subset of A, mu E f d mu equals 0, then f equals 0 mu almost everywhere on A. And this is where f is just some complex valued and obviously measurable function. So to prove this, the only neat way that we were able to think of to prove this was to just do a contradiction argument. So assume for a contradiction that f is not 0 almost everywhere. Then assume, without loss of generality, that n and m are natural numbers such that, so here we're going to call this set E. The set E defined by the set of points where a real part of f is greater than 1 over n and the imaginary part of f is greater than 1 over m. Yeah. So this is the set. Such that E equals, this satisfies mu E is greater than 0. That's because basically what we're arguing is, let's look at the range of f, and this is on the complex plane. This is the real axis, this is the imaginary axis. So we've got some weird set, which is the range of f, and we really don't know what it looks like. It can be some weird set, it can have point masses, it can be kind of fuzzy, it can have open sets in it. It doesn't have to have like any real nice properties at all. But what we do know is that it has positive measure. So it must have positive measure. Well, the real axis and the imaginary axis both have 0 measure. So it's got to have positive measure either in one of these 4 quadrants. And if it has positive measure in one of these 4 quadrants, then we can kind of take a slice of this quadrant such that the stuff that we cut off in here in this slice has positive measure. Because if we weren't able to do that for some slice, then the measure of the set intersected with this region would be 0, which would go against the point of what we're doing, the choice of this quadrant. So we just choose another quadrant. So basically we're just assuming without loss of generality that we've got real and imaginary parts positive because, I don't know, I guess the first quadrant is nicer. But one of these quadrants has to have contain a portion of the set which has positive measure. But then if we look at this, if we integrate over just the set, then that integral of f d, let's see here, d mu here, here, I should not have called this mu. So if, what's a good name? Sigma. I never use sigmas for measures. So anyways, let's use this. And sigma is just some positive measure. So it's not signed or anything. We don't have to worry about that. So if we're integrating a function on a set of positive measure where we've got this nice property of f, like f takes values in that first quadrant, then this because this measure is positive, the integral has to take value in this quadrant. And in particular, because this region is bounded away from 0, it's not equal to 0. This is a contradiction. Right. Yeah, and let's see here. Right. And the other thing is, I'm kind of assuming here that E is a subset of A, because I said f equals 0 mu almost everywhere on A. So what I'm saying is assume for contradiction that f is not 0 almost everywhere on A. And so that range, that picture that I drew, we are kind of assuming the whole time that the region that we're looking at is only the region that lies in A, because that's really the only one that we care about. But anyways, this is a contradiction, and so that gives us the proof of our lemma. Now, to prove this, and now I know that I have this in the right direction, because in my notes I have suppose nu is mutually singular with respect to mu, which is this. Okay, so we're all lined up now. So again, let x equal A disjoint union B, where now we have to remember what this means for complex measures. This means that A is nu null and B is mu null. And I just realized something. So mu A prime equals mu B prime equals 0. This is for all A prime subset of A and B prime subset of B, and thus this. And that's really important here, because this definition requires these sets A and B not just to be 0, but to be null, which means that all subsets are null. But to see that this is equal to 0, this is actually pretty straightforward, because nu here, the absolute value of nu, what we could do is we'd look at the absolute value of nu of A prime is less than or equal to this of A prime, and this is a positive measure, so here we can do this, but that's equal to 0. And likewise, we could do the same thing over here. This, less than or equal to mu of b is equal to 0. See, man, even though this is my second time recording this, I almost really messed up this proof. So yeah, you really have to be careful and make sure that you have these definitions straightened out. So this and thus this. So I'm sorry if you were watching this earlier on and you saw me do this and you were like, no, that's wrong. Hopefully you watched up until this point before you decided to like yell at me in the comments. So I was in the middle of a sentence here, I think. So where A is nu null and B is mu null. Yeah, I was at the end of a sentence. So now let E be some set such that lambda E is equal to 0. Then for all... Oh man, I really messed up this. Here we go. Wait. Yes. Okay. So, we don't want to do this. What we want to say is then for all, because now we want to prove that these two are mutually singular. So we don't have to worry about like all these arbitrary subsets and stuff like we had to do earlier on. All we have to look at is find a Hahn decomposition basically of our space. Well, not Hahn decomposition, but let's decompose our space into a place where nu lives, or a place where norm nu lives, and a place where norm mu lives. By norm I mean absolute variation, total variation. Okay. So, then, for all epsilon, which is a subset of A, 0 is equal to nu of E. That we already know, because E is a subset of A and A is nu null. But then by the chain rule, this is equal to the integral over E of d nu d nu d nu. Right? Because this is just the integral over E of d nu, and you just add in the d total variations of nu's. And then, so by our lemma, d nu equals 0, norm nu almost everywhere on E. I'm just going to call that norm nu. But by 3.13b, this thing is equal to 1 nu almost everywhere. Thus it must be that nu of A equals 0. That's the only way to reconcile these two facts. Right? You know what? Do we even need E? You don't even need E. Just get rid of it. Grading A by our lemma. This. So be that lambda A equals 0. Here we go. Likewise, you do kind of the same thing, but you with nu replaced by mu and A by B, total variation mu of B equals 0. So hence, total variation of nu is mutually singular with respect to the total variation of mu. And there we go. And then we're done. So, can I fit the next part here? I don't think I can. I'm going to have to scroll down a little. Here. For the next part, suppose, I'll scroll up a little bit so that we can see the statement. There we go. Suppose nu is mutually singular with respect, no, absolutely continuous with respect to lambda. Let lambda e equals 0. Then by definition, and again, these definitions, you got to keep these in mind. What this means that if you were to break up the measure nu into its real and imaginary parts, then these two would have these measures evaluated at e would be 0. That's what it means. That's what this absolute continuity means. But then, total variation of nu of e is equal to nu r plus nu I of e, and we just use the triangle inequality. I'm not going to write the absolute values because the stuff that we end up with is going to be positive. But these two things are equal to 0, and so their sum is 0. So hence, total variation of nu is absolutely continuous with respect to lambda. Conversely, if we know this, write nu equal integral of f d lambda by Radon-Nikodym, because we've got two positive measures. One's absolutely continuous with respect to the other, so we can write this. Then nu, by definition, is the integral of the norm of f d lambda. So let's see if I can fit this on this last line. Let lambda equals 0. Then, let's see here. What is nu of e? Absolute norm nu of e. This is just the integral of f d lambda, but this has to be 0 because lambda is 0, and we've got this absolute continuity. So f equals 0, lambda almost everywhere on e. I don't think I'm going to... Oh, I might. So... Here, let's do this. So norm of f, and thus f is 0 almost everywhere on lambda is 0, lambda almost everywhere on e. So 0 equals integral over e of f d. I wrote a mu, that should be a lambda. That's just nu of e. Okay, there we go. I was able to fit it. So nu of e equals 0. So we know that if total variation, if lambda equals 0, then nu e equals 0. And so nu is absolutely continuous with respect to lambda, and that proves this direction. And so we have finished the proof. One more thing. I realized I made a mistake. So I said this thing about us not needing e. That was completely wrong. What happened was I had written in my notes nu almost everywhere on e here, but in fact it needs to be a here, so I was wrong in my notes. But we do need that for all e in a. 0 equals nu e, blah blah blah, because that's exactly what our lemma says. Our lemma says that if for all subsets this holds, then everything holds. So this is the final statement, and I guess I was just trying to think on the fly, and that's really difficult to do, especially when you're presenting a solution. So just wanted to make that fix, and now we're good.